One of the popular boosting algorithms is AdaBoost, short for adaptive boosting. It was proposed by Robert Shapiro and Joab Freud in 1996. AdaBoost was the basis for all subsequent research in this area. Its main advantages include high speed. As the construction time of the composition is almost entirely determined by the learning time of basic algorithms, ease of implementation, good generalized property, which can be further improved by increasing the number of basic algorithms, and the ability to identify emissions, the most heavy objects Xi, for which in the process of increasing the composition of the weight Y take the largest values. Its disadvantages include the fact that AdaBoost is an algorithm with a convex loss function. So it is sensitive to noise in the data and is prone to overfitting compared to other algorithms. Stacking reinforces weak classifiers by uniting them in a committee. It has gained its adaptability because each subsequent classifier committee is built on objects that previous committees have misclassified. This is because correctly classified objects lose weight, and incorrectly classified objects gain more weight. In Box 1, we assign weight levels to all points and use a decision stump to classify them as pluses or minuses. This weak classifier generated a vertical line on the left, D1, to classify the points. We see that this vertical line incorrectly divided the three pluses, classifying them as minuses. In this case, we give these three pluses more weight and apply this classifier again. In Box 2 we see that the size of the three incorrectly classified pluses is larger than the other points. In this case, the threshold classifier of solutions, D2, will try to predict them correctly. And really, now the vertical line, D2, correctly classified the three incorrectly classified pluses. However, this has led to other classification problems. Three minuses are incorrectly classified. Let's perform the same operation as in the previous time. Assign more weight to incorrectly classified points and apply the classifier again. In Box 3, the three minuses have more weight. To correctly distribute these points, we again use the threshold classifier, D3. This time, a horizontal line is formed to classify the pluses and minuses, based on the greater weights of the misclassified observation. In Box 4, we combine the results of classifiers D1, D2, and D3 to form a strong prediction that has a more complex rule than the individual rules of the weak classifier. And as a result, in Box 4, we see that the AdaBoost algorithm classified observations much better than any single weak classifier. Note that when the basic algorithm works well or does not have the wrong classification, it leads to an error of 0 and a relatively high value of C. When the base classifier classifies half of the points correctly, and half incorrectly, the value of the coefficient C will be equal to 0 because this classifier is no better than random assumptions with a probability of 50%. And in the case where the primary classifier constantly gives incorrect results, the value of the coefficient C will become quite negative. There are two cases of alpha function. The value of C is positive when the predicted and actual results coincide, i.e. the point has been classified correctly. In this case, we reduce the point's weight because the work is going in the right direction. A value of C is negative when the predicted result does not match the actual result, i.e. the point was misclassified. In this case, it is necessary to increase the point's weight so that the same erroneous classification is not repeated in the next classification. In both cases, the basic classifiers are dependent on the result of the previous one. We will use the dataset of the University of Belgium compiled in 2017. This dataset contains information on electricity consumption throughout the house and temperature and humidity in the house and weather conditions, temperature, humidity, pressure, wind speed, etc. on the street. The idea is to classify high and low electricity consumption depending on the weather and learn to predict what the consumption will be depending on the weather. After preparing the dataset, we will review the distribution of electricity use. We see that the average value is 100 units, which is why we will divide our dataset into two parts: low, up to 100, and high consumption, more than 100. Classification will take place on 25 parameters, and the type of consumption will be defined. We see that the prediction is more accurate, which means that AdaBoost is appropriate and profitable to use in this case. In general, the improvement is more than 10%, which is a very good result. In conclusion, we can say that the effectiveness of ensemble boosting methods compete with neural networks, but they are somewhat more stable and understandable, which is why they have an advantage in choice. Also, the AdaBoost algorithm can slightly improve the result compared to strong classifiers. However, there are cases when even a difference of 3 to 5% is significant. This can be said in the example of Google, which uses AdaBoost in search results, as well as Apple, Amazon, Facebook and Microsoft, which also use ensemble methods, simply do not publish their algorithms. They do it because it is financially profitable. And then even a few % improvement is valuable. That is why this algorithm will be further developed and used.